Last time we looked at exponential growth functions. This time we're going to look at exponential decay functions. Alright, so we're going to go ahead and graph this example. G of x equals 4 times 1/2 to the power of x. Right? Again, we know this is an exponential function because the variable here, is the exponent. Right? So when we have that up there, we know it's going to be exponential. Right? So this will be similar to what we looked at before, but it's going to be a little bit different. Okay. All right. So again, let's do a t-chart, an input-output table, and again, let's go from -4 all the way to +4. Right. And just like in our last video, I will do some of this, and you're going to do the rest of it. All right. So I'm going to go ahead and again start in the middle and see what happens here. Okay. So let's figure out what's going to happen when we input 0 into our function. Right, well, we're going to get 4 times 1/2 to the 0th power. Right, 1/2 to the 0th power is 1. So this is just going to be 4 times 1, which is 4. All right, so when we input 0, we get an output of 4. Let's do g of 1. Let's figure out what happens when I input 1 into my function. So I get 4 times 1/2 to the 1st power. Right, well, 1/2 to the 1st is just a half, and then 1/2 times 4 is 2. So g of 1 equals 2. So when I input 1, I get 2. Let's do another one. Let's do g of 2. When I input 2, I'm going to get, let's see, 1/2 squared here. So a half squared, this is going to be 4 times a 4th, right? A half squared, that's just 1/2 times 1/2, that's a 4th. So a 4th times 4, that's going to be 1. All right, I'm going to do one more. Let's see. One more positive one. Let's do 3. G of 3. So that's going to be 4 times 1/2 cubed. All right, so let's think about that. What would that be? This is going to be, g of 3 is 4. A half cubed, what is that? That's 1/2 times 1/2 times 1/2. Right? So 1/2 times 1/2 is a 4th times a half, that's an 1/8. So this is going to be g of 3 equals 4 times 1/8. Right? 4 times an 1/8 is 4/8, which is 1/2. Okay, so when I input 3, I get an output of 1/2. Okay, I think I'm going to do one more of these, and you're going to finish the rest. So let's do g of -1. So this is going to be 4 times 1/2 to the -1st power. Right, so g of -1 is 4, let's see, 1/2 to the -1st, this is going to be 2. So 4 times 2 is 8. Right, so when I input -1, I get 8. All right, I've done enough here. I would like you to finish the table. Okay, so do one more positive one when you input 4, and then do the negative inputs here, -2, -3, -4. Let's see what you get. All right, go ahead and pause and do that. All right, so actually, I think let's check, make sure you guys did these. I'm not going to show all of them, but I'll do a couple. Let's do what happens when I input 4. All right, well, when I input 4, I'll do that over here. G of 4, I will get 4 times 1/2 to the 4th. Right, so that's going to be g of 4 equals 4 times, this is going to be 1/16. Right, and 4 times 1/16 should be 1/4. Right, and then maybe I'll show my work for just one more of these. Right, let's do -2. So when I input -2, g of -2 is going to be 4 times 1/2 to the -2nd. Well, 1/2 to the -2nd, that's just going to be 4. So g of -2 is 4 times 4. So g of -2 is 16. All right, and you should have finished the rest on your own, right? And these, you should have 32 here, and you should have 64 here. Okay, so we have kind of a similar pattern to the exponential growth, but it's not exactly the same, right? Let's go ahead and graph these. Right, for our scale, again, I'm going to use a different scale on my x and y. So x, again, will count by ones. So -1, -2, -3, -4. And then for the output, for the y-axis, yeah, again, let's go ahead and count by tens. So 10, 20, 30, 40, 50, here's 60, etc. Okay, so let's go ahead and graph these. So when I have an input of 0, I have an output of 4. So 0, 4 is about here. 1, 2 is about here. 2, 1, that's getting smaller. 3, 1/2 is about here. 4, a fourth is here. Right? On the negative side, when I have an input of -1, I have an output of 8. That's about here. When I have an input of -2, I have an output of 16. That's about here. And then -3, 32. Let's see, 20, 30, 32 is about here. And then -4, 64. That's about here. Okay, so let's see. Here's what our function looks like. All right, so this pattern is kind of similar to the exponential growth, but it's kind of reversed, right? We have really big values over here, right? As my x values get really, really negative, right? -1, -2, -3, -4, right? This side is going to be really big, right? This is 64. The next one's going to go off the graph, but if I had an input of -5, this would be at 128, way over above this graph, right? So this side is really big, but then it gets really, really, really small, right? For over here we have 2, and then 1, and then 1/2, and then 1/4, and then it would keep on going to be 1/8, 1/16, 1/32, right? This gets really, 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 really small. But again, just like exponential growth, as it gets really, really small, it's never going to reach 0, right? It's going to be really small, 1/2, 1/4, 1/8, 1/16, 1/32, really, really small, but never hit 0, right? Never go below that either. So just going to get really, really small on that side. Last thing I want to talk about is just kind of comparing exponential growth and decay. So we've had one video about growth, one video about decay. So how do we tell the difference, right? So this is what our growth graphs look like, and this is what our decay graphs look like, right? So again, we've kind of seen this difference, right? As our x values get big, then this is going to get really, really high really fast. Right? Decay is backwards. It's high over this side, and then as x gets big, it gets really, really small on this side. Okay? So how do we tell the difference between whether something's going to be growth or decay? Right? Well, growth equations will look like this. Right? Let me write a couple of these. 3 times 5 to the x, or maybe I'll have 1/2 times 16 to the x, or maybe I'll have y is equal to 7 times 1.03 to the power of x. Right? Decay equations will look like this. Maybe I'll have y is equal to 5 times 1/2 to the x. Or maybe I'll have 3 times 0.8 to the power of x. Right? So I want to see if you can see the difference here. Right? These would be growth. These would be decay. Right? What's the main difference? Right? Well, what they have in common, first of all, is that they're all exponential. They have an x value for the exponent. But what's different is this factor inside here. Right? Growth graphs have a factor inside here that is bigger than 1. Right? 5, 16, 1.03. Those are all bigger than 1. Right? Decay graphs will have a factor that's less than 1, like this, 1/2 or 0.8, right? Or some other fraction or decimal, right? Less than 1, right? When this number is bigger than 1, that's going to cause it to grow as x gets bigger. And when we have something that's less than 1, that's going to cause this to shrink, to get smaller and smaller as x gets larger, right? And it makes sense because, just for example, think about comparing this. Y is equal to 2 to the x versus y equals 1/2 to the power of x, right? If x were 3, then I would have 2 times 2 times 2, right? I'd have 2 to the third here, right? And here I'd have 1/2 times 1/2 times 1/2, right? If I had x equals 3, right? So if I have 3 factors of 2, 2 times 2 times 2, that's 8. That's going to get bigger, right? Versus if I had 3 factors of 1/2, I'm getting smaller and smaller and smaller. Okay, so the big thing you got to know is for your growth graphs, when this factor is bigger than 1, it's going to be growth, and it's going to look like this, right? Get bigger as our x gets bigger, right? For decay, this factor is less than 1, and it's going to get smaller and smaller and smaller, but never quite hit 0 as x gets bigger.